Hi everyone. We're going to get started with the webinar today. I'm going to be your presenter today. I'm Tim Coyle. I am the founder of Signal Bytes Technology, and today's webinar is going to be an IBIS model repair workshop. So at any time, if you guys can't hear me, or if you have any questions as we go along through the material, feel free to use the webinar question box, and I'll answer the questions as we go along. I got a couple of slides I'm going to go through as a quick review, and then we're going to go right into doing some interactive reviews of some IBIS models. So hopefully you guys will find this all very interesting, and we'll have some good Q&A today. So like I said, I'm the founder and lead hardware consultant at Signal Bytes Technology. We provide hardware engineering design services, signal and power integrity, embedded hardware design, and I also develop and license a suite of signal integrity design rule check tools, and the first one is IBIS DRC, which goes beyond the IBIS parser and does a lot of built-in quality checking. So let's talk about today's webinar. So for today, I'm going to do a quick review of an IBIS model and of an IBIS model quality flow, and this is going to kind of dovetail off of the last webinar I did about a week and a half ago, the 7 deadly sins of simulation with IBIS models. And I think most of the people on the webinar today attended that, which is good. And if you haven't, you'll see a quick review of it. And then we're going to go right into looking at some IBIS models, looking at the issues, and starting to understand, how you assess the quality levels of IBIS models, and then what you can do to fix some issues, and what you can do, or what can't you do to fix some issues as well. So we'll get into that. So overview of an IBIS model. So this is your classic block diagram of an IBIS model. So we're showing a classic push-pull driver here. So you've got a pull-up and a pull-down. Those are represented by some IV curves. You might have an output clamp stages, your ESD structure, and then a simple RLC package. Right, so the IV and the VT curves, these are more like lookup tables. Remember, IBIS is a behavioral model. And this really represents the I/O buffer, right? So a good replacement for SPICE model. And there's also an I/O capacitance associated with the model as well, both for whether it's an input or an output model. And then again, we've got a simple RLC for the package model. And then when I just look at the IV and the VT curves, and we'll spend a whole lot of time on this because we're going to go look at some models, but one way to look at it is your IV curves are basically set up as sort of variable resistors. So this sort of sets your drive strength of your driver driving high and low. And then the VT data is really used to kind of as a switch, right, to decide, by the simulator when to turn, your NMOS on and your PMOS off and vice versa and all that. So this is kind of a rough overview of how it's all put together. Hopefully you guys are familiar with all of this. And like I said in the last webinar, I kind of went over what an ideal quality check flow is, right? And the first step is run the IBIS parser, and this is kind of your first line of defense. But you don't stop here, because IBIS parser, really is more of a IBIS specification compliance checker, just making sure that everything is in there, that needs to be in there at a basic level. But there's lots of things that it can't check for. And there's lots of, what I'm going to say, ambiguity in terms of checking something and determining whether that's a quality model or not. And so we'll take a look at that today. And then you should always check your package pinout. So if this is a 20-pin device, all 20 pins should be in there, properly defined with the RLC. This is really important for post-layout analysis. So if you bring, these models into your post-layout board tools and run simulations, lots of times you're going to need to have the full package there. You should view the IBIS, IV, and VT data. There's a lot you can learn by looking at the data structures. You can find errors quickly, so it's always good to get an intuitive sense of these curves and how they're working. Run custom model quality checks. So this is really kind of going beyond the IBIS parser, where you come up with your own quality check. Like, for example, maybe you want to check that the output impedance of your driver, the pull-up and pull-down, are, within 10% of 20 ohms based on the data sheet specification. That's kind of the idea, is to bring in extra stuff that the IBIS checker doesn't do, add in a bunch of stuff that you can get from the IC data sheet, and then you can have a much higher confidence that your IBIS model is going to be good. And then you should always simulate the IBIS model. You know, you can start out into a test load, maybe do a simple transmission line load as well. But really what you want to do is simulate it, you know, into some sort of test load before you drop it into your full level simulation. That way you know the model's good before you go and start simulating, and then you've got to debug a whole simulation flow, whether it's your package models, your PCB models, with the tools. So it saves you a lot of time and stress to do it like that. And finally, you can correlate the IBIS model. And there's various ways to get data, whether it's through the IC vendor or your own lab measured data. It's always a good idea to bring that data back and correlate the IBIS model. Okay, so that was a 5-minute overview of IBIS models and the quality flow. Okay, so now we are going to here we go. Get out of PowerPoint and go into IBIS DRC. So this is IBIS DRC tool. I'll show you. There'll be some things in here that are specific to this tool, but in general, most of the stuff you can do with any IBIS editor view or manual checking and stuff. So what I'm going to do first is we're going to open a sample IBIS model. So this is just a DDR3 I/O model. Okay, and this is one that I've already run through the tool. So I'm just going to show you really quick kind of how the flow would work in an ideal situation with a good model, and then we're going to go on and look at some broken models. Okay, so if you run the IBIS parser, it's going to come in here with no errors or warnings. Notes are okay in general. And then this is kind of what I call the command center in this IBIS tool. It's basically an editor that gives you access to everything in the tool. Now, in an IBIS model file, you have this notes section, and basically you can put in anything here you want. All tools ignore this. And sort of this is where I recommend and where you'll see most IC vendors, if they leave you any notes about the model, are in the notes section. So in here, and obviously it's got a little tool that allows me to track notes and revisions and stuff. So this is good if you work a lot with IBIS models, multiple people maybe. You can figure out who's checked it and who's done what. So just a little tip, use the notes section. That's what it's there for. And then I talked about looking at the package, right? So I can give you guys an idea of kind of one way that you might want to look at checking the package file. I need to find the spec files. Here we go. So I got created this as a simple little example, but basically what this is going to do when I run check with no errors, it's going to look at pin 1. It's going to check the signal name, right? Make sure it's the right signal name, and then make sure that the model type is right too. So it should be ground to power, and then this DQ buffer should be bidirectional. And so, like, this is what I'm telling you about when you need to check your package pinout section. Now, of course, this is just a simple example, 3 pins. There could be 30 or 300, but you want to make sure that these are things that the model type and that the pin number matches the pin versus the data sheet. And like I said in the last webinar, you can do this with Excel scripts and stuff. So there's different ways to do it, but that's kind of the checking that you want to do. Now, so that kind of shows you, running the IBIS parser, making sure that there is looking at the package section, and then the next part will be looking at the data and then running some quality checks. And once you do all that, really what you want to do, and this IBIS DRC creates an HTML report, so really what you do is get a final report. And I'll just give you a quick overview of it. You got some header information about the IBIS model file. There's some quality definitions, which I'll come back to in a minute. Here's your IBIS parser results. And then here, there's only one model in here, but if it had multiple models, it show you multiple models. And here's just basically a big HTML table of a bunch of stuff, right? So these are all the checks that the tool runs for you. Now we're not going to go over all these today, in detail, but this is an example of sort of how you would start your checklist. And some of these are based on the IBIS quality checklist, and some of these are internal to the tool. So if we come over here, and this is a good section to look at, this IBIS quality definitions. So there's something called IBIS quality checklist. And the idea is there's a subgroup within the IBIS working group that came up with sort of this checklist to say, okay, if the IBIS model has these certain data in it that's validated, and if it's simulated, it's a test load and validated, we'll assign quality levels to it. So there's all these quality levels. And I really won't go over them with you guys. You guys can look at this afterwards and look at the IBIS specification. But really, this is a way for you and your company and your group to start to sort of what I would say bin models, you know. So, for example, a level 0 model means that you shouldn't simulate it. Ideally, you'd like to have a level 3 model, right? And a level 2 model, you know, might be good enough to do basic simulations, okay? But it might not have the right test loads for time analysis. So it's really not so important if you follow this necessarily, but it's probably a good idea if you're going to start checking models to come up with your own quality rating. Because some models are going to be so bad you won't be able to simulate with them, and some are going to be so good that you'll be able to simulate with them. Okay, so let's go back to the tool. Okay, so that's just a quick overview of the quality levels and stuff. And now this is the quality checker built into IBIS DRC. And what this is this is sort of a snapshot view. And on the left, it's showing things that are being pulled from the IBIS model across the process corners. And you guys saw me where I selected the spec file, right? So the spec file is just a text file you create, and you put in some variables data here from your IC data sheet. For example, you know, I've got the test load in here, this VREF, CREF, RF. You can specify your package impedance, VT frequency, so you can look at this to figure out if your IBIS model is overclocked. And then there's a bunch of things in here, preferences that you can set that checks for additional data items that the IBIS parser doesn't do, okay? And then you run this, you're going to get some pass and some fails, and then we open this report, and you can see this was the report I showed you guys earlier. And then you can see you've got a bunch of things in here that pass, fail, or ignore. So like I said, I've already run this model through so I know it passes. And here it automatically assigns the quality level for you. And so, you know, this is sort of the automated way to set up your checklist, okay? And so I'm not going to run all the models today through this quality checker per se. I just wanted you guys to show you kind of what the flow would look like. And so if we go in here and we show the graphs of a model, and so we talked about the IV curves of looking at the pull down and looking at the pull up, right? So these are your different, you know, your PMOS and NMOS driving, and you get your IV curves, and then you've got your falling and rising VT waveforms that you can look at as well, okay? And so you can look at these curves, make sure that they're there, and you know, make sure that they're right. Okay, so that was sort of the sample good one. So let's go and let's look at some models. So what I have is that 4 models here. We'll see if I can stay on task and not get off on too much of a tangent. I can get through all of them. But again, feel free to ask any questions as I go through this. So let's open up this first one. So what I did is I tried to go. These are real models generated from different IC vendors. They're available publicly on their websites. So I tried to get rid of their company names because I'm not here to bash any particular company. This is just learning exercises. So what I'll do is I would just walk you guys through how I would check a model, and then I'm going to talk about things I find and kind of tell you why that might be an issue and why that might not be an issue. So again, the first thing to do is to run the IBIS parser. So here, there's no warnings and there's no errors, so that's good. And this is really where things start to happen. Because at this point, when a lot of people do this, is they might say, okay, there's no errors. I could take this model, my simulation tool, start running simulations, and I'm good to go. Well, okay, why don't we why don't we stop for a minute and look at a few things and make sure. So, what we can do is we can come in here and just load a spec file that's not set for this data sheet, right? So this spec file is just a generic, LVTTL output. So, it's a 3-volt one, and this is 5 volts. That's why you're seeing some errors. But if you run the quality checker, if you run through your checklist, you can start to come in here or look at your own checklist, and you can see some things that might start to fail. So we start here, so for example, we see that the ground clamp might not be right. So let's go back. Actually, what I want to see, you can choose the model type. So there's multiple models in here. I actually want to look at the output model. So this is the one that we want to look at, okay? Okay, so this is the one we want to look at. So if we come in here and we start looking at things, we can start to see, I gotta minimize my other screen here. We can start to see that there's some failures here in terms of the edge rates. And one example is this ramp time rising, where it says that the ramp time mismatch is bigger than measured. And so what the IBIS parser does is it looks at the ramp DVDT data, okay? And it looks at whether that time measured from the VT data is measured 20 to 80, and it compares it. And so this is one of the things that's a little ambiguous is the IBIS parser might use a 10% error, and sometimes that causes too much of a edge rate difference for you, okay? And let me show you what I'm talking about. So if we come into this output model and we go into ramp, okay? For example, what this is saying is this is a 2080 time measured off of this VT waveform of whether it's 50 ohms to VCC. You measure the 2080 edge rate, say on this red curve, which is your max one, and this value in here should be within 5%, right? Now sometimes, like I said, the IBIS parser, depending on which version it is or where it's at, I think it always uses 10%. But if you run your own checks, you can dial it back to say 5% if you want to. So this is just an example of how you can kind of set some of your own custom quality checks if you want to, okay? Another thing to note in here is you look through here, you're not seeing the full timing test load, okay? So if you guys remember, when we look at vMedge, if you guys remember that the time to clock output in IBIS model, the standard timing load, is supposed to be into some sort of load, a resistor, a capacitor, combination load, into some sort of test load, right? So they might do like a capacitor to ground, and then you measure the time it takes the driver to cross this threshold. So this vMedge value is in here, but what's not in here is the timing load, okay? So what's going to happen is some tools are going to interpret this as being an open. Some tools might give you an error. So when you're doing your flight time delays, this is going to potentially give you some problems. Now you can see that the IBIS tool doesn't give you a warning or an error on it. It's the IBIS parser's got sort of its own subset of rules, whereas if you put different values in here, it'll give you some rules. So if I come in here and try and put this in 5 volts, and we run it, let's see if it'll, so you can put some values in here, and it'll be okay. But the point is here is that it doesn't necessarily check that these are the right values or that the full load here is applied. So this is a case of where you want to look at this, if you're using flight time delays, and check it either manually or through a script or a tool, okay? And again, this is something that the IBIS parser won't catch for you. And I can see one right here, and I'll show it to you here. If we look at the C comp of this, you can see there's a value for typical, but there's not a value for min or max, okay, even though we've got min and max column data. So probably what's going to happen is this typical value is going to be used across the tool for both min and max. So remember, this is the output buffer capacitance. Now, this isn't necessarily going to cause an error in the tool, but it is going to use what I'm going to say is probably not the exactly right capacitance value. And so, this is a case of where you're going to need more data. You're going to need to probably simulate the output of simulate this model, and maybe get some correlation data to figure out if these min and max values need to be there to get an accurate result. In this case, since this is kind of like a generic T-tail output, it's probably not going to make a big difference. But if you don't have correlation data, sometimes you aren't going to know that. Okay. So that's another thing to look out for. This is a common one that you'll see a lot, is where you're not going to get the full C-comp value, or what you're going to see is that it's the same value. So if we go look at an input model, so in this case they did it the same. The input model doesn't have the min and max value defined. So if you think about this, now you've got your input model, which has input capacitance, and you're driving a load to it, and now the min and max corners, they're going to use the typical capacitance. So you're not going to see the worst case now. So that's going to not give you the most accurate signal integrity results, right? So it makes a bigger difference for your input when you look at it in that situation of looking at the signal quality. Now again, how much of a difference is it going to make? Will it be 2%? Will it be 5%? I mean, I don't know, right? You would really have to, again, at this point, probably ask the vendor, why they didn't put that values in if they have them, and ask for some correlation data. So these are the sort of things that you can start to look at, right away, and then start understanding that the IBIS parser just isn't able to check everything for you. And I'm going to show you one more on this guy, because this is a good example. So here's the rising waveform. So this is a VT waveform. So this is just showing it going from 50 ohms to VCC. Now, if you guys are looking at this, what you can see is that there's some transition points around 6.5 nanoseconds. It stops about 11 nanoseconds, and then they've explicitly added a data point to get it out to be 20 nanoseconds. Okay. And you can see that there's no data points, nothing transitions till about 6.5 nanoseconds. So probably what happened is whoever developed this model was trying to force this time window to be 20 nanoseconds, right? Because essentially this time window, if you guys remember, defines the max frequency of this IBIS model switching. So they're probably trying to make this switch, at 10 nanoseconds or like 100 megahertz output, right? So what they're trying to do is the data sheet says that the TCO there should be 5 nanoseconds. They're trying to force it. And when reality is you don't want to do this. You just want to grab the transition, and when it reaches steady state, you want to cut it off as much as you can. Because remember, this time in IBIS model takes the transition internally always gets subtracted out of a flight time delay. And if you make it too long, then you can get into an overclock situation where if you want to switch to, say, at half this frequency, it'll be right here, and then it wants to transition from a high to low. And then some of the simulators will have problems with that. So really what you want to do is you just want to take this chunk of data. So really you could do this within 4 or 5 nanoseconds instead of 20. The rest of that data you don't need. And again, you really need to simulate this, with your desired input frequency to make sure that it's going to simulate fine. You won't have an overclocking issue. But that's sort of how you could check the overclocking issue in an output model. Let's see. So if we go back and we look at that model, so this is the output 51. So you can see here, right, based on the typical data, 20 megahertz is the maximum that you could switch at. So you have to look at the IC data sheet and see, what is this supposed to switch at? What are you going to be switching at? If you need to run it faster than 20 megahertz, in this case, you would want to try and fix that data. And so, like I said, if we go back to that, you could delete these first data points, right? And then shift the whole thing over. And let's see if I can do that pretty good. Now, normally, what you should do what you should do is really ask your vendor to do it, because they're the ones who've got the data, and they're the ones who, should understand the I/O. So most of the time, I don't recommend, fixing data like this by yourself. And let's see if that removed it or not. Yeah. So I should keep that 0 point in there. You always want to start at time 0. And I'll take it out. Yeah. We would have to do more editing here. So, this is kind of the problem of doing stuff on the fly interactively. Hopefully it's good and you learn stuff, but sometimes you don't do things exactly right. So really what you would do is add one more data point here. That would be 0. But shift this point to start at 0. But I think you guys can kind of see what you could do is you could easily shift this data just by quickly editing the curves, and you could just delete these guys on the end, right? And then that would shorten your timing window, and then you wouldn't have an overclock situation. But remember, you got to do it for all the curves, right? You can't just do it for one. You got to do it from all, and you got to move them all at the same time. So if you delete, 3 nanoseconds from one, you should delete 3 from the other. So that's why I said it's really better for you to do this, have your vendor do it. But that's one way to do it if you have to do it, if you can't get the vendor to do it. Okay, so that was it for that one. So hopefully you guys can kind of see as you go through and look at some of these that you got to go beyond the IBIS parser. And some of the stuff that you look at might seem like it's okay, but you're going to have to decide if that's really true or not. So now I'm going to open up a different model. So this is another one. So again, we run the IBIS parser, and we see that there aren't any errors, which is good. So let's go and, again, in these situations, I'm just using this generic spec file to get a quick look at something. So we're going to look at this 8 million output driver. And so you can see here that in this case, they've got the test load defined for you. You see a CREF, RF, and vMesh, so that's good, right? And so, in general, this model looks like it should be okay so far. So let's go take a look at a few more things. So these are to pull up and pull down impedances. Again, you can see by doing these types of quick checks, you can get an understanding of what the drive strength and what the range is, and the sort of drive strength mismatch between the pull up and pull down is going to be, like, for example, this type of output driver. This is the one I wanted to show you guys. So this is not, and the IBIS parser doesn't check this. This is something that I'm checking for in the GRC tool. We're checking how many points are in your data curve. And so for this instance, for your IV curves, you only get 19 points, and you can have up to 100. And so one of the reasons why I check something like this is to make sure that there's actually, valid data in this output model. So let's go and graph this. So you can kind of see, if you look at this pull-down curve, is that they've got data, starting at 0 volts, and then they go through up to about 3 volts. So they go from 0 to VCC volts. And they've got, and we got some data points in here. And when it comes to how much data points do you need in an IBIS model file, it depends. There's sort of this question of, the pull-ups are saying, there's sort of this question of how much data is needed, and it's really kind of based on how a simulation, how you write an algorithm. And ideally, you want to have more data points, say, where something transitions versus where it's just flat, okay? So in this case, you can't really say that there's not enough points. But one of the reasons I put those types of checks in is so, for example, you don't have to waste time, or miss something, because sometimes you'll see where someone will make what I call a data sheet model. So they'll try and make like an IV curve based off of a data sheet or a data book transistor curve, and you might see something like this. It'll be 4 or 5 points, and it'll just be linear. And you know that it's not actually made from simulation data, it's made just from a data sheet, and it's probably not going to be that accurate. So this is another type of check that you can look at to make sure that it's okay, right? So now you've got these different data points here, and you're going to have to decide if that's good or not. And the way to decide that is to simulate it, and I'll show that in a minute, okay? If we look at this, here you can see we've got, this problem is so common that I actually have a check, you know, I didn't show it, it's in the spreadsheet, where it looks to see if C comp is the same across all corners. So again, you can see they put in the same exact value for your tip, your min, and your max. And again, you know, how much problems or how much trouble that's going to cause you is going to, you know, it's going to depend on this I/O, the types of simulations you're doing, but in some ways it's starting to show you that there could be other issues with this model, that they didn't, you know, take the time, or they didn't understand that, you know, you need to have, you know, the corner capacitance of your die buffer model in there as well. So like I said, you're going to see that one a lot. So I put that in there. And let's go back to the checklist, because there's one more that I wanted to look at. And where is it? Where is it? Yes, the ramp rate. So you can see here that it's failing on the typical, right? So this is your DV, DT, so this is a ramp time. And, you know, I didn't explain it in the last one, but what happens typically is the simulators look to see if there's your voltage time waveform, okay, the VT waveforms. And remember, those VT waveforms define, you know, how the switching occurs between your pull-up and your pull-down, essentially. If the VT data isn't there, then the simulator tool defaults to the ramp data, which is not as accurate as an actual voltage time waveform, because it's essentially just an edge, a 2080 edge rate value. But it needs to be there. And what happens, you see this sometimes, is people put them out of order. So, you know, this is your min, this is your tip, and this is your max. Your typical is faster than your max, right, which isn't correct. So it's got the wrong value in the wrong column. And again, this isn't something necessarily that the IBIS parser can check for, but it's something that you can check for. Now you might say, well, most of the models might have VT waveforms, so it's not going to use it. I should be all set. Not necessarily true. A lot of the signal integrity tools use that ramp data as sort of an estimate of how fast the edge rates are of the IC in the system. And some of those are used in you know, some of the other calculations or field solver properties in the tool. Not all the time, but you know, so just make sure that you have the values there and that they're in the right order. Okay, so we talked about that. So let's go and run a simulation. So what we're going to do is we're going to run this simulation of this 8 milliamp output. Because remember, we saw that it didn't seem like it only had 20 or 30 data points. C comp is the same. There might be some issues. We're not really sure. So what I'm going to do here is I'm going to run a simulation. And we're just going to run this, you know, with the 50 nanosecond period and run it with an input edge. And what I'm doing here is obviously you can plug into external simulators. So we're plugging into IBIS. We're going to create some sample SPICE files. It's running IBIS right now, and then we're just going to open up this data and view it. And let's see. Hold on a minute. I didn't want to run an edge. I actually wanted to run a pulse input. So I want to see a couple edges switching. So let's just rerun that. And open. So if you look here, what we're showing is, you know, your 3 corners, tip, min, max, you know, just running a simple pulse input into the standard low, which is a capacitor low. So it seems like it's switching is okay until you go up here and you look at this output voltage, 0.001 volt. Okay. So essentially, what's happened is this output is not switching properly. Okay. So this is a good example of how you can go through an IBIS model and even identify some potential issues, I'd still think it might be okay to simulate. But then when you go to simulate, this one doesn't simulate at all, okay? And there's not a fix here for this. You need to go back to the IC vendor and say, I'm simulating the IBIS model into a test load in my tool, and I don't get a valid output at all. And the reality is there's some other issues with this IBIS model. I won't go into details, but it's a bad model. There's some wrong data in here, and it needs to be totally redesigned, or it needs to be fixed. And this is something only that the IC vendor could do. So in this case, you couldn't even use this model to do simulation. But if you think about it, right? If you came in here and just ran the parser and saw that there were no errors and went on your way, and then you've got your full system and you try and run simulations and you're not getting any output at your receiver, you would have to go through and debug all this, right? So this is the advantage and the benefits of doing these types of quality checks, up front before you go off to do all your simulations, or in parallel, right? So this is sort of the flow that you would want to use, no matter what tool you're using, or if you're doing manual checks, right? You can kind of pick and choose based on your schedule and your experience and your time of looking at certain things inside of IBIS models, looking at these curves, getting an understanding of where there might be issues and where there might not be issues, and then doing the simulation and correlation, running the simulation before you do your full level simulation to catch big errors like this that are going to cost you a lot of time to track down and debug. Okay. So that was that one. Let's see. Let's go on to the third one. And you're going to find, some of these, you're going to find issues with a lot of IBIS models. A lot of this stuff you're going to see over and over again. And you get used to, fixing them, or you're going to get used to having a good flow to, document the issues, send it back to your IC vendor, and have them fix them for you, okay? So in this case, when we run this model, we're getting some warnings about power clamp curves not reaching 0. There's no errors, but there's 9 warnings, okay? So let's go and look at, I think it was this one. So this is an input, okay? And you can see here, oh, look at this. See comp is the same across all of them. That's a very, like I said, I see that so much that I added a custom check in the tool for this. You're going to see that all the time, So, what that means is they probably didn't do any type of correlation or measurement on it, right? They just got an estimate value and used it across the corner. But discuss them for another time. So you've got this ground clamp curve here, and what the IBIS parser is trying to tell you is that this never reaches 0. Now remember, your power your ground clamps are essentially supposed to be like the input ESD structure, right? So what that means is a little bit below ground, right? Your clamp curve should turn on, and a little bit above VCC, clamp curve should turn on, and that's going to protect the input circuitry of your I/O. Now what happens, right, though, is in between, right, in between, say, minus 0.5 volts and 3 volts of VCC, this current should be 0, right? Because as long as you don't have an ideal diodes, right, you should have 0 current. And it's really hard to see. It looks like that it's 0, but if you really zoom in, right, you can see, for example, these are your process corners, tip, min, and max, that you've got a little bit of current here. We've got like 0.001 to 0.003 amp, so you've got a little bit of current there. So something like this, what this normally means, I'll show you. What this normally means is this is probably a IBIS modeling formatter. So whoever created this model, either through simulation or data manipulation, subtracted a few things, and they didn't get 0, You know, sometimes you subtract two really small numbers and you get a really small number, even though you're expecting 0. So the reality is that the IC, the I/O input in the IC probably works fine. It might be 0, but the way that the model was created is not giving you 0. And so, you know, this is a warning, okay? And so what happens is you'll see a warning in your simulation tool. And this is one of the things we're told, okay, is this going to cause you a problem or not in your simulation? You know, it depends on the tool. It depends on your simulation results. You know, again, this is one of the things where you really can't fix this yourself. Even if you did zero it out, you might change the characteristics of the clamping when it turns on and off. But again, you got to go back to the IC vendor and say, you know, you guys probably have an error with this. You should fix it. You know, and if you can't fix it, then you're going to have to decide if it's a big enough issue for you that you don't want to use it for simulation. And another way you could kind of tell that that was a numerical error is if you go and look at the way they did their power clamp, and you know, essentially what they're saying is their power clamp should be really small, it should be essentially 0, but you've got a few data points out here that, again, you know, for me, since I've developed models myself, when I've worked at companies and I've used them and do it for consulting, I see this stuff all the time, so I kind of understand, you know, that this is a numerical error. And you can see you've got a couple of wayward points here, you know, of how these are causing you problems, right? And so, you know, you could try and edit these points, you know, if you wanted to, or you could go to the data line in the editor. So there's different ways you can try and edit these types of points. You know, you could try and edit this out, you know, if you wanted to. So that's one way to you know, kind of look at these types of curves and figure out what's going on, get an intuitive sense, and be like, okay, this is more of a numerical issue error. Maybe you can edit, you know, you could edit these out quickly yourself if you want to, or go back to your IC vendor and have them fix it. So again, this is another issue. You know, you've got an input model, and it may or may not be that good for you. You're going to have to, you know, go through your process, assign a quality level, and determine, you know, what's good enough for you to use and what's not. And again, you could ask your vendor for correlation and say, hey, show me this IBIS model input receiving a signal, you know, something driving through the transmission line into this, and compare it against, you know, the SPICE model you made, or show me lab data, show me that the clamping and this input structure and the die capacitance is working the way you expect and properly, right? So that's where the correlation data always kind of comes into play. And so what else do we got here? And so we've got some output models here too that you can look at. You know, you've got the same CCOM problem. You can look at, you can start to look at the pull down and power clamp of this output structure as well, okay? And you can kind of, you know, start to see, you know, does it have the right, you know, the right curve that you expect? And then you can try and start to simulate stuff like this, right? So let's see. Again, so if we want to look at something like this and just run a quick simulation, you know, and see what it's going to look like. So we're going to look at this output, because everything else seems like it's okay. So I want to show you guys one that actually simulates here. There we go. Right. So let me turn off all the corners except for the min corner, which is your slow corner. So you can kind of see here's your slow corner transitioning, you know, up to, you know, 2.85 volts, which is the VCC in the min corner. You know, it's going to be whatever, -5%, 10%, whatever, fine. Switch to 0. So this one looks okay. You can kind of see that it's having a little bit of trouble driving up. There's kind of a glitch here, but things like this you really can't tell, whether this is an issue or not without correlation data. So if you had a lab snapshot from your own bring-up board, silicon validation board, evaluation board, you could kind of see that this is what the circuit would look like. But ideally, the IC vendor would give you some correlation data for this, right? They would show you this data, the test loads, and you can see waveforms, say, overlaid, right? And sometimes it's helpful to take something like this and then go and look at it with a transmission line load. And so what I'm going to show you guys here real quick is driving this same circuit into a capacitive load with a transmission line, right? Because now I see it looks like it's having trouble driving, and what I want to see is what does it look like driving a transmission line? Because sometimes you see more with it driving a transmission line than you do with a standard load, right? And so what I'm doing here is, I'm using this form to fill out it driving a 10 picofarad, right? So it's going to be 10 picofarads with a transmission line of, say, a nanosecond, and then, 50 ohms, okay? And so hopefully I did that right, and we'll run some simulations, and then we can view the data. Boom, there you go. So again, if we go through, or, this is a good case, you can see the green is your fast corner, red, or in this red here is your tip, and then blue, so I'm going to say, is your slow. So you can see that because we're, a fairly long transmission line, a nanosecond, which would be a couple of inches, right? The max corner does, maybe some termination would be good in this case, but it seems like it's driving enough. Tip is slowing down. It's slow. You're really starting to push the boundaries of this driver in this case. You're almost getting this sinusoidal waveform here. So this is sort of an advanced thing of more like, even though you're working with IBIS models, you can start to do some design simulation, do some design analysis. You can start to figure out, what can your driver drive in terms of a system load? Would you need termination? And you can quickly do this type of stuff in your tools, even before you start to do your full level simulation. And so that's just sort of ways that you kind of use your IBIS models to go beyond it. Okay, so that was that one, and I got one more left. I know, probably I'm covering a lot of information here today, but this will be archived, just like the last one. You'll get a link, so you can go back and rewatch it. And if you don't have questions today, you can always email or call me after, and we go over stuff with you, no problem. So what I wanted to do is I wanted to show you this one because, again, this one doesn't have any errors, but it's giving this classic warning of AC-DC mismatch. And I actually should have put a slide together for this, but what this AC-DC mismatch is, and you see this one a lot, is it takes this load, so we've got 50 ohms tied to 1.2 volts on this output, okay? And so what that means is it's, it's transitioning from 1.01 volts to 1.42 volts. But when you take this 50 ohms to 1.2 volts and you apply it to the IV curves, you do a load line analysis. You guys remember back to your days of doing stuff like that in engineering courses or whatever. You get different DC endpoints. So the endpoint should match. So it should be, if you apply the same load on your voltage time to your IV, you should get that same load endpoint. And this is what I call a data integrity check that the IBIS parser does. And it's a good one because you see this mismatch a lot, okay? So what model is this? This is a 33CP. 33CP, so I think it's this one, right? So if we come in here, right, and look at the rising waveform, right, So again, this value is 1.01 volts. And this value is roughly 1.42 volts, okay? So again, 1.01, 1.42, but when you apply that same load to your IV curves, right, one of them, your pull up, your pull down, isn't matching, right? So if you do the IV curves on this, right, I should give you a slide to show you how to do that calculation, right, to calculate what the equivalent endpoints would be. Is you're not getting the right ones. And now that you're looking at this curve, this one looks kind of funny, doesn't it? And I'll tell you what, I could tell you exactly probably how this model was created, because you can see there's a bunch of data points, say from a little bit below ground to, to VCC, is either their models or maybe a lab data. They extended all the way out with that data point. And here it looks like they tried to extrapolate where the clamp curve would be, or extrapolate down that they wanted to go to minus VCC when necessarily they might not even have to. So this might potentially be a problem. But again, what's happening is, the load line should match here, and it's not. And so what that means is when you simulate this, it's going to give you one or the other, right? So in reality, if the real IC is supposed to be, say, 1.01 volts, it might give you 0.98 simulation, or vice versa. Let's say it's really supposed to be 0.98, but it's giving you 1.01. So what you see is you start to see, these voltage low and high, really DC mismatches, right? And that's a problem because that's going to shrink essentially your noise margin. If you're expecting, this is obviously it's an LVDS signal, so the output signal under swing should be 400 millivolts. Well, if you start losing 10% of your voltage swing because of a model accuracy issue, that's not going to be good for you when you try and figure out your margins. So I'm running a little bit out of time, so I won't go through the finish to simulate it. But again, this would be a case where you'd want to simulate it, okay? And it would be a case of where you want to get the correlation data for it, okay? So that was kind of a whirlwind of various IBIS model quality issues that you will run into. And what I hope you guys saw today, and what I hope you realize is that, one, you need to go beyond the IBIS parser, right? Because just because you run this and you don't see any errors doesn't mean there's not problems with the model. And two, there's these what I'm calling custom quality checks in here, okay? And these quality checks, again, if you guys saw in the last webinar, you got to automate this. But you can see that there's just way too much in here to try and do by hand all the time, right? So you got to start automating, scripting it, or like I started way back when. Start with a manual list, eventually move to automation. You got to start checking at least some of the major things, like the timing loads, the die capacitance, right? And if you kind of mix that in with looking at these curves, right, even if you just flip through them, you can see data points that are way out of whack. You can see that there's no data at all. There's only 3 points. You can start to quickly understand, if you need to spend more time with the model or not, if it's got quality problems. And the last thing, again, is really the simulation piece, okay? And you really want to simulate this and, determine whether this is going to be a problem or not. And what I'm going to show you last year is this sample model where there's this test data keyword in IBIS, and you can load in essentially waveforms from anything. And this is a great place to put correlation data. And so what I'm doing in the tool is I'm using the same test load that the SPICE model is used in. I'm going to run the IBIS model in it. And what's going to happen is we're going to upload and compare the data. Now in this case, right, so here's my IBIS data switching to the process corners. And down here, I've got this test data I can upload. Now the test data was used a different pulse pattern. You can see that it had a different input pattern. So this stuff isn't going to match up necessarily for the tip corner, right? But you can kind of see that that's the idea that you want to have is to be able to load in your simulated IBIS data and compare it to something, or at least look at a few of the metrics like the edge rates and stuff. And for example, in IBIS DOC, you know, I have it set up so I can plug in the different tools that I can support, like IBIS and stuff. But if you have something, you know, a different tool, you can always load in the data manually and stuff. You know, and you can do this in your own tool, your own waveform viewer. You know, some of this stuff is just an automated flow, but I think you guys can kind of see that, you know, you can run your own simulations no matter how or what you're going to do it and compare it to something. You know, just take the edge rate of your simulated IBIS model and go in the lab and look at it on whatever bench you have and see if it's within 10%. So you can always start somewhere to look at the IBIS model quality. You know, and I think, you know, as you do more signal integrity or how deep you're into it, you're going to, if you haven't already realized it now, is that correlating your simulation model to your hardware is really what closes the loop and gives you the most benefit of doing signal integrity in the first place. So you always want to close that loop. And IBIS models and the I/O models that you use is part of that, just like your PCB impedance and transmission and S parameter models, all that stuff. You need to kind of close the loop and make it so it all correlates, and make sure that you understand how every piece in your flow works. And so again, that was really it. That's what I had for today. And so I hope that you know, I hope I didn't go too quick. I hope that this was a little bit more made more sense sometimes than just looking at the slides. To kind of understand what the problems you run into with IBIS models and kind of what you need to do to fix them, and why you need to go beyond the IBIS parser and do some simulation, and always ask for correlation data. Okay, so that's what I had for today. Do you guys have any questions at all? Anyone have any questions on any of the specific models or anything else that I went over today? Any questions at all? Not today. Everybody's still dealing with it being Monday, so that's okay. I can understand that. Well, listen, I appreciate for you guys attending. Thanks for your time. And again, you'll get an email in a couple of days, or maybe even tomorrow, depending on how quick I can get this up, if you want to rewatch it. And as always, feel free to contact me offline, send me an email, give me a call. I'll help you out with any IBIS problems you have. So thanks a lot for attending, and I hope you guys have a good rest of your week. All right, thanks a lot.